I recently set about writing a couple of shorts about Brontosaurus, and I wound up with 10 pages of notes, of course, because it turns out that the neck and the armor have some really interesting implications for sauropod physiology. A lot of people, or at least people who comment on our shorts, tried to correct us and say, that's not Brontosaurus, that's Apatosaurus. And like 10 years ago, there was a paper where they went very granular, trying to look at the evolutionary relationships of a bunch of animals that we at the time called Apatosaurus, and they found that there were two monophyletic clumps. 2 or 3 species of Apatosaurus were more closely related to one another than any of them were to the at least 2 species formerly called Brontosaurus, and vice versa. So resuming the use of separate generic names was pragmatic. I'm going to talk about this more when we get around to re-uploading our Apatosaurus video, but there are objections to calling those species Brontosaurus, but they come from people who object to using specimen-level phylogenetics in this way for this purpose, and I am not prepared to explain that today. This paper, or at least the news that Brontosaurus is back, actually made a pretty big splash at the time, like on social media and even in conventional media, but I guess even that was not enough to overwrite, what, 4 generations of, well, really, you should call Brontosaurus Apatosaurus from people like, well, people like me, if I'm being fully honest. These Brontosaurus toys have pathetic little necks. No sauropod could have gotten away with a neck this long if it were shaped like this. Sauropod necks were actually built more like a trussed crane boom, where as the span of the neck increased, the muscles and ligaments needed more leverage to hold it up and to move the neck around. But they couldn't just scale up the bones that their ancestors had because that would be too heavy, and because that's so much more bone for the growing animal to have to build. Bones aren't free. You know what's free? Air. It was the diverticula that expanded, those air sacs throughout its body and skeleton that it already had due to the way that it breathes. So the bones were able to sort of inflate and get the mechanical advantage they needed for a fraction of the weight and with a significantly lower cost in minerals and nutrients. There's recent research looking at soaring birds where they found that by inflating and deflating a diverticulum in their chest, they can actually finely tune the leverage of a particular muscle that they use. And I wonder if there might have been something like that going on with sauropod necks. There's a lot of muscles and ligaments passing right next to a lot of big diverticula. But regardless, for a neck this long, you need a wide air-filled frame, not a noodle. So why did it have sacs in the first place? Well, it was partially because of their unidirectional flow through breathing. I've mentioned this occasionally without going into detail about what it is. Our lungs are tidal. We have these reservoirs at the ends of ducts where the air stops so that the blood can exchange oxygen for carbon dioxide. Archosaur lungs just vascularize the ducts themselves. They divide the bronchi into many tiny parabronchi. This means that they can do gas exchange on the go. Archosaurs can get away with this because the lungs are partially affixed to the rib cage. They have that skeletal support so they can have thinner, more vascularized tissues all through here. In crocodiles, and seemingly the ancestors of sauropods, the front, more rigid portion of the lung, the part affixed to the ribs, is for gas exchange. The rear, more flexible portion is for pumping the air in and out. It appears that sauropods, like birds, moved the pumping organs outside of the lungs entirely. We can tell because this correlates with diverticula, with air sacs invading the bones, which is crucial for scientists because lungs don't fossilize. How it worked was almost certainly different from living avian theropods, but it was probably the same steps. The first inhale pulls fresh air past the lung proper and into the rear sacs. The first exhale pushes the fresh air through the parabronchi. The second inhale pulls that spent air into the front sacs, so the second exhale can push it out of the body. Because it's a 4-stroke process, taking 2 inhale-exhale cycles to complete, there are 2 breaths in the system at any given moment. They're sort of juggling air through their bodies. This had another advantage. Having a lot of air in your neck can also be a hindrance. As a sauropod was growing up, long before the bones were in danger of breaking under their own weight, it would run into trouble breathing because of something called the dead space problem. The windpipe itself holds a volume of air, which the animal has to push out of the body before the spent air from its lungs can leave, and then pull in before any fresh air that it's inhaling can reach the lungs. For animals like us with tidal lungs, there is a limit to how long our neck can get before the energy required to take a breath is unrealistically high, or the amount of volume we need to make up for the dead space with each breath is impossible. Whales have ways of getting around this, but they are aquatic and therefore cheating. Because they only take a breath every once in a while, they've had some wild changes to how their respiration works. They can collapse their lungs way further than we do, so when they exhale, they're pushing a lot more dead space out of the body anyway. Their muscles store more myoglobin, which means that they have more of a buffer before the blood has to deliver more oxygen. And some diving whales have an air sac system, apparently for buoyancy control, which they can use to shunt air around in their bodies to keep the level of oxygen in the air that's in the alveolar chambers at an acceptable level. Sauropods, despite being about the same size as some whales, were terrestrial, and their metabolisms were not burning nearly as hot. So the solution they came up with, as you probably already guessed, was their flow-through lung ventilated by air sacs. Air sacs, and possibly diverticula, hold more volume, so the animal can take up and play out more of the slack with each breath. The efficiency of parabronchial gas exchange means they can still make use of stale, low-oxygen air that does get re-inhaled. So actually, I lied earlier, our sauropod would have no trouble at all mitigating the dead space problem. I do feel the need to clarify something at this point, because a lot of people commented on our shorts just saying giraffe, like it was some kind of gotcha. This is a giraffe. This is a Brontosaurus. This is a Diplodocus. Did I mention that this toy is supposed to be a Diplodocus? It doesn't look like one, it looks like a Brontosaurus, but the person who sent it to us claimed it was a Diplodocus, so I'm not going to disagree. Giraffes and sauropods are dealing with some of the same physiological challenges, but can you see how sauropods might be at an entirely different magnitude? The largest giraffes are males 10 or more years old. They're approaching 2 tons. A 2-ton Apatosaurus isn't even half of adult length, and it's something like 1/10 of its adult mass. It hasn't grown quite so rapidly as the giraffe has, but it didn't have a head start, spending 15 months in the womb. It's probably like 12 or 13 when it reached this size. And yet, look how much more skeleton it has, and how much more it still has to make. Not to belabor the point, but building out your skeleton gets exponentially costlier as you get larger and larger, unless you can leverage your air sacs. Giraffes are the reason that I say that a tidally breathing sauropod would have unrealistic energy requirements. Giraffes mitigate the dead space problem by narrowing their trachea, which means that the volume is reduced because it's just a smaller circumference. But if you've ever tried to breathe through a coffee stirrer or something like that, you know that you have to work a lot harder to get the same volume of air in and out. Giraffes have these long elastic fibers in their lungs, which mean that they naturally contract to push the air out, and they can immediately start inhaling, reach maximum inhale rate faster, and take a longer inhale. They take like 2 to 3 seconds to inhale, as opposed to less than 2 for the exhale. Giraffes can afford to do this because they are eutherians. We run hot, but we burn a lot of energy to do it. Sauropods, while certainly higher metabolic level than other reptiles, were still lower than a giraffe. Unidirectional breathing actually occurs in a number of living ectotherms. Savanna monitors and iguanas both have it, and neither of them have particularly long necks. These differ from the archosaur system. It appears that they don't have as much specialization between the front gas exchange portion and the rear pumping portion. The unidirectional flow is kind of a consequence of just the way the airstream sloshes around the chambers, but this may have advantages for a low-energy lifestyle, because any motion that pumps the lungs even a little bit will cycle fresh air into the gas exchange portion, even if it's just the animal laying there having its heartbeat push the air around. You're still getting a little bit. Again, sauropods have correlates for a much more sophisticated respiratory system than that, but the principle is the same. The efficiency gains of a flow-through lung are present even if you are a lower energy animal. These toys are both fairly old-fashioned depictions of sauropods. The narrow, low-slung neck with a big, wide head on it, the splayed front limbs, the overall bell-curved back. I was surprised, therefore, to see osteoderms represented on it. But it turns out sauropod osteoderms were known back when this kind of depiction was state-of-the-art. In the middle of the 19th century, Mantell described the impressions of the skin of a sauropod from Britain that appeared to show a pavement of ossicles. It later turned out that these were actually just scales. At the turn of the 20th century, Desparet described a large, flat osteoderm from a sauropod from Madagascar. But then in the 1920s, that was reinterpreted incorrectly, it turns out, as ankylosaur veins, as were any subsequent sauropod osteoderms that we came across. It wasn't until 1980, with the description of Saltsaurus, that sauropod armor was incontrovertibly established. And this toy, in a surprising twist, post-dates that discovery. This toy was made in the 80s, and I don't know if the manufacturer intended this, but the arrangement of the osteoderms as a sort of evenly spaced set of nodules over the entire back of the animal is consistent with how the describers of Saltsaurus thought its armor was arranged. So it's actually pretty accurate for a Saltsaurus at that time. If only they hadn't labeled it Brontosaurus. There's actually a decent amount of artwork of Brontosaurus in particular with skin armor. I don't know if it's ossified, but it's not on the back, it's on the underside of the neck. As sauropod necks got longer and longer, their cervicals became narrow struts and thin walls between a bunch of air-filled chambers. Then, Apatosaurines, like Brontosaurus, went and enlarged the solid portions anyway. They developed these uniquely overbuilt neck ribs, as well as reinforcing the struts that they connect to. All sauropod necks are more of a trapezoid in cross-section than they are a circle, but Brontosaurus and Apatosaurus take it to an extreme. They developed these like off-road bumpers at the bottom. Some workers proposed, 10 years ago now, that this might be an adaptation for elephant seal-like shoving matches, where the animals are pushing against each other with those bumper necks. But as far as I can find, that idea has never actually been published as peer-reviewed research. So the only sauropod armor that we have really attested is from titanosaurs. It came in a variety of shapes and sizes. The arrangement on this toy is probably not what was going on. It probably was not just simple rounded nodules like this. Also, I'm treating this as if it is a Saltsaurus, even though I know it's a Brontosaurus. Saltsaurus's armor was mostly tiny ossicles, only half a centimeter to a centimeter across, forming a pebbly pavement. It's similar to what we see on the throat of Stegosaurus, and at this toy's scale it would be invisible. The larger osteoderms are not just simple domes. Paper most of this is from calls these plates, but these are not upright plates like on a stegosaur. These are like dinner plates. They're flat circles or ovals with a nub in the middle. Personally, I would have called them rondels, and the rondels that we find in Saltsaurus had something interesting going on with their bone tissue. When a titanosaur's armor started growing in, there were a couple of different ways it could go about actually building the bone. The usual situation is called metaplasia. The cells that usually build and maintain the skin started making bones now. We can tell because the osteoderms still have the fiber bundles that were once the collagen of the skin. They've just turned to bone. That structure is what we find in the tightly packed ossicle pavement and on the outer portion of the larger rondels. But then the base, the sides, and the insides of the rondels are different. They appear to have grown the way that the bones of the skeleton do. There's a core of spongy and woven bone tissues acting as a blood vessel highway, carrying everything the bones needed to remodel the outer layers of the osteoderm as it expanded. The authors thought that this might just be because the rondel was just so much bigger than the little ossicles that it needed that nutrient highway to transport all the stuff that it needed to maintain and expand and remodel the armor. But I wonder if something else might be going on, because other saltasauroids had even more extreme remodeling happening in the bottom, the roots of their osteoderms. We literally need to go deeper. There's a bone bed of titanosaurs from Spain, consisting of Loecatitan pandafilandi and Cuncasaurus pintiquinestra. These are excellent names, very fun to say. They're also Don Quixote references, so Well played, Spain. But the Loeca-Titan material includes many large osteoderms, apparently arranged in parasagittal, that is, lengthwise rows along the animal's back and the base of the tail. The outer portion is about what you would expect. It's the familiar bulb or plate shape, but underneath the skin, they form these, like, bone carrots, these enormous roots just under the surface of the hide. And when they scanned the insides of 17 of these, 8 had long empty channels down the middle, and 4 had low-density spongy bone around those channels, forming cavities extending down the root. It's kind of like what we saw in Saltsaurus. It's almost like the dense spongy bone had been vacuumed out, leaving behind these chambers. Now, what could make an osteoderm look like that? Well, remember when I said bones aren't free? Well, neither are eggs. And if you, a Saltasauroid, are gravid, first of all, congratulations, but you have replaced any bone in your body that you can get away with air pockets. So if you want to pull nutrients from your bones, pull calcium from them, that could be life-threatening. You're a very heavy animal. You can't risk the structural integrity of your bones, not even for your precious eggs. So instead, like modern crocodilians, you're going to mobilize the minerals in your osteoderms, in your armor. It occurred to me that because the embryos are going to be building their skeleton by dissolving away the inside of their eggshell, when it hatches, a titanosaur is carrying its mother's armor inside it, in a way. Sauropod growth was one of the most extreme processes vertebrates have ever come up with, and I love when workers find this or that seemingly minor detail of their anatomy was integral to making it all work. And I want to thank you for watching Your Dinosaurs Are Wrong. Please remember to like, comment, and subscribe, and we'll see you next time. We would like to extend a special thank you to these individuals who have gone above and beyond to support this show. We could not have done it without you. Thank you.